How's it going, everyone? Ooh. Welcome. Euler Gonzalez here again, fighting now with one of my threats. Alright. But in today's video, we're going to focus on the front-end system design. So, since this is a course taught by Evening Ray, and we want to look now is at this particular section that are relevant, especially for UI developers. Now that once you decide to be a UI specialist, right, front-end engineering, it is important to understand now what are the roles that you need to take care of, especially when you're building this front-end system application. So because at the end of the day, the thing here is we want to know what are the fundamentals that we need to know that allows to build these web scalable applications. All right. So it means that for our case, right, which is the front end, an application is made of backend, API, and a front end. For front end, we have now 4 areas according to Evening Ray where we need to take care of. Okay. So Evening Ray is the software engineer that works at JetBrains for over 3 years, and now he's currently working at Meta. Okay. So the idea here is that by understanding what are the features, the responsibility of our role, we can now deliver fast. We can now actually provide much more deliverables to this. So in our case, we are responsible is for the API communications, how we're going to communicate to this API, as well as how we're going to store is the data and manage that data management, and how do we deal some of this advanced and complex user interactions, okay, for marketings or virtualizations or adding dynamic elements or lazy loading using the interception observer, or when it comes to now detect when the user changes an input, or for this text-rich editors or graphing tools, we can use the mutation observer. So for example, companies like Notion actually are using this mutation observer, and for responsive design or for graphing tools or charting tools, we want is to now make those elements, those graphs, those visualizations responsive across different viewports, right? Whether it's mobile, tablet, desktop. So that's why we use is the resize observer, and when it comes to actually put everything in place as a way to understand what is the core fundamentals of building these front-end applications, we also need to know how do we manage our assets. In this case, the relevant assets are the HTML, CSS, JavaScript, font, image. So this is a very interesting course, right? We went over this as a way to explain that all of these different nifty details that we are going to use as we evolve in our application and developing all of these kind of applications, right? But what we really care about in today's video is now, so far we have looked at the UI data, so the core fundamentals, right? And we started to see how we're going to handle is the data management layer, or the application state and network. So here we are. So Evening Ray mentioned that here we're going to discuss about how we build the UI in our application. How we build the UI in our applications. So with that, there are the data that we store in our API has two properties. Again, all of this is based on what are the data that we're gonna store and how do we gonna handle that, right? How we gonna manage that. So for that, we need to know is what are the type of data that we're gonna store and manage. Makes sense, right? Makes sense. So we have now the use case, we have now the data classes, and it is property. So for the data classes, we have is the type of information that we're going to store is from the UI, whether it is data that we store based on the configurations, okay, theme configurations, localized font size, accessibility settings. This is one of the class of data that we store. Also, the UI elements state, which is, hey, do we select all of these selecting controls or selecting text? For example, in Google Docs, when you actually select a particular text like this, okay, so you select this text and then you want to apply some particular, let's say this one, right? Some particular font size, right? There you got it. Lovely. Okay, so this is data that now Google Docs actually store that. Okay, one of the type of data that is stored, the UI state, and also the another type of data is the server. And I think starting from this basic explanation is something that is very, very interesting. Why is that? Well, because we're starting to see what is the problem that we are solving at the end of the day. So what is the problem that we're solving? And describe that problem. So once we are able to understand that, so we can now understand much more about the problem and then provide some sort of solutions for that. And this is one of the things when we are looking at one of the area of responsibility when building this UI, the UI applications or this scalable UI, right? And the other data that we need to store and handle, the data class, is the server data. Okay, so data that come from a message, let's say real-time data or posts, right? Data that come from the server. And each one of those classes are data. Okay, we can think of these classes of data as our baskets. Okay, where we're gonna put this particular data here as a way to help us to organize much more better. And each one of those baskets, data classes, has its own properties. Okay, which means is that how is this data is gonna be accessed, the access level, the access data. Hey, is this data should be accessed per components or globally? The other is how many times we're going to write or read this data in our applications, because depend of how many times we're going to read this data, whether it is on the UI, whether it's on the whether it's on UI state, okay, whether it's on okay, so whether it's in app configurations or UI element states or server data. So the thing here is how often are we gonna read or write on this data? Okay, so for example, if you plan to read and write the data a lot, so it will actually block the main UI. So you might want to find as an alternative to do that, right? And I think this is some quite interesting challenge, especially as you serve for this kind of applications, okay, especially for big giant companies, where they see this as something that so they're going to invest is on things that they drive them money, okay. Well, that's interesting. That's laudable. That's actually part of the business. But one of the things that most of this company cannot foresee is that these open source applications actually provide huge tons of values, not only to developers but also for the company itself. But in any case, because a lot of the time they are solving is recurring monotonous tasks. So in any case, but this is now the properties that are relevant, especially when we need to handle this data management. Okay, so what are the type of data that we're going to store? All right, this is data classes, which can be configurations, user themes, or locals, or fonts, or accessibility, or local state. Okay, so for example, selecting of checkboxes or selecting a text, okay, local state, UI local states, or the server, right? But each one of them has its own properties that we need to take care of. So for example, it's like how often this data is going to be accessed, right? Or how often this data is going to be read and write. Okay, because if you need to do that, so if this particular data you need to read or write this data frequently, you might end up blocking the UI threads. So to prevent that, we are going to rely on some sort of mechanisms or techniques that allows to help us in that. So it's important to consider is we need to decide whether this data should be left on a runtime memory or other storage. Interesting. As a way to provide is this fast access, fast read and access data, and the other is the size. How heavy will be the size of data that we need to store here? Okay, so because the length of the data, it means that it will impact on your CPU to parse and read or write on top of that. So again, all of this is just to consider when you are doing the data management, the type of data that you're going to store, okay, and how each one of them has their own property that are going to enable is general principles to manage the applications, which is we want to minimize the access cost. Of course, we want to minimize the access cost, the search cost, as well as the space or the space, which is the memory RAM use. Okay. This is now the principle of this application states based on how we're going to store and manage our data and its properties. So what is the end goal that we want to achieve when we're managing the application states? So reduce the read cost, or minimize the access cost, as well as the search cost or read cost. So access cost, search cost, and the size of this, which is minimize the memory usage. Okay, slowly but progressively starting to make a lot of sense. All right, so let's keep going here, right? Shall we? Okay.
So more things we store in the application, the more.
Yeah, one of the issues that I saw, and I think again, we're not perfect. Of course, I am not perfect. I wasn't be able to describe all of the things that I'm doing. And I wasn't be able to speak in this clear way and fashion, to transform all of these complex ideas and image into meaningful sentence. I wasn't able to do that. Not at all. At least in the last, back in 5 years ago, I wasn't able to do that. But now with constant exposure, practice, and most of the time understand what's true, then you realize like, okay, I don't need to fake it. I don't need to actually follow all of these conventions that North American actually say. It's like fake it until you make it. Just do it. That kind of sentence, from their marketing. It's like actually is because you truly want to know the truth of all of this, then this is the thing that you need to do. This is the process. This is the stuff that you need to do. And most of the time, it won't be easy. Not at all. It won't be easy. It won't be easy. It won't be easy. Unless you have some rich patterns that can give you all of these kind of things. But most of the time, it won't be easy. And this is when the character is built. Because it actually now exposes you to what it is. Not what it should be, not what it must be, what it is. So. Okay. Let's get into this. All right.
Let's discuss. And if we have it, although so we have the memory usage. The more things we store in the application, the more likely we're going to utilize too many objects, and we can easily bloat our.
The question is that, well, actually what I'm going to do is to take note out of this video. You're not able to see what I'm looking right now because I don't want to receive any red flags, okay? But yeah, I'm just going to transcribe that to the docs.
Our RAM.
So the question is that, fine, you're good. So now that Yivni tell us that, yes, if you want to manage your data, the application states you need to know what is the type of data that you're going to manage, okay, what are the classes of data that you're going to manage and store, all right, and what is its properties. Because with that, we can define now what is the end goal of managing this application, okay, and therefore understand what we need to do, how to do that. Right. Okay. So now that so now that we can describe. This is quite important. Okay. So now that we can describe thanks to Yivni. Oh my God. Yivni Ray. Okay. He must be Brazilian, right? He must be Brazilian. Yivni, yeah, a Brazilian, yeah, or a Paraguayan, yeah, totally. He must be from Paraguay, yeah. Thanks to Yivni Ray, okay, so now that we can describe thanks to Yivni Ray data management, therefore state management, okay, which is how we going. What are the data what are the data we are going to store and access, okay? So what are the data that we're going to store and manage,
Okay.
okay? That's right. So now that we can describe things to evening rate data management, state management, which is what are the data? What are the data? What are the data that we are going to store and manage, right? So what are the data that we're going to store and manage? So that's why exactly what are the data that we store and we manage when building UI, when building complex UI apps. Okay, so I think I lose myself a little bit. Okay, so now that we can describe things to evening rate data management, state management, which is what are the data that we're going to store and manage when building complex UI. All right. That's right. So when building complex UI, such as data classes, like so what are the type of data that we're going to exactly, such as data classes or types. Okay, for example is app config. Okay, app config, UI state element, as well as server data, right? So far so good. Good, absolutely good. As well as it is property, properties, which is access level, how many times we're going to access, how many times we're going to read and write this data, which is read and write frequency, and based on that we're going to decide when do we want to store this data, whether it's on RAM or in other devices or in other storage, and the size of this data, right? Frequency. Okay. So all of that is to know why. All of that is to know what is the goal of data management, of UI data management. All right, of UI data management, which is, okay, all of that is to know what's the goal of UI. All of that is to know the goal of UI data management. Okay, which is exactly, all of that is to know the goal of data management. Minimize so is minimize. Okay, so minimize read, minimize risk cost, minimize exactly, minimize read cost, minimize access cost, minimize memory usage, right? So that's the end goal of this. Okay. So the goal of data management. The goal of UI data management. Right? Is all of this. So the goal of data management. And how now that lead us is to, well, understand now an example. So let's take a look at an example. Right. So this is the example. All right. Good.
So let's get the practical kind of example. So we have the Messenger app where we render the contact list, and each contact has a conversation where we can have thousands of messages potentially. So, and how would you optimize that? So the most obvious approach would be just to put everything into the contacts state and the global state, but there is a problem with that. So if we want to access a contact with ID Jane Smith and we want to find any message with ID 5, then we're going to do two hoops. First, we're going to filter out the contacts. Then we're going to filter out the messages. So this is although acceptable, it's still not the best way, because if we have potentially thousands of messages, then we need to traverse the whole array just to access single element. This is not the way we want to design our app. And so the first technique that we can use to optimize our data is to change how we store it. And there is a concept called data normalization. So the data normalization has been around for, I think, 20 or 30 years already.
30 years.
So it's a concept used in the databases heavily. The
For
goals
the
of data normalization is to provide optimized access performance and also provide the optimized structure how we store the data. And if we have a unified structure how we store things in a state, it increases the readability of our code and further maintenance. And the data normalization operates with the normal forms, where there are in total 7 normal forms, and the more the farther you go, the more you normalized. In the UI apps, we usually utilize only 2 or 3 normal forms, and let's go for the process of data normalization. So if we take the first example where we have a simple object with the ID and name, and then it has the job and the location. So right now it's a non-normalized object. So we can optimize this by applying the first normal form. And what the first normal form does is tells us that every field on your object should be atomic. So we need to convert to reduce any nesting in our objects. So we just flatten the nested objects here. So the job object becomes the job ID and job title, and the location becomes country code and the country name. Also, the first normal form tells us that they should be the primary key, and we know that we already have the primary key, which is the ID that we can utilize. So the next, we can convert our first normal form to the second normal form. And what the second normal form does, it tells us that all our fields now should ideally depend on the entity. So if we look at the following fields, the job ID and job title, the job title actually depends on the job ID, although it also depends on the on our user object. So the data normalization tells us that we need to decouple this into the separate table in the database concept, but in our case, it will be a separate object. So we move our jobs, we move our job to the jobs table. Now we have the key, which is the UIE as a job ID, and now we have the information relevant to this job. And we also normalize the user jobs, so we can access what type of job the user has by providing the ID. So this is now all our entities depend on the primary key. There is a third normal form. Also we moved the countries to a separate table. There is a third normal form that tells us the main difference from the second one. We say that non-primary keys should depend on the entity primary key. But the third normal form enforces this rule, saying that it should depend only on the primary key. And the difference is very subtle. So if we look at the UI job, it has a title and department. So department really might not be directly related to the UI or to the title. So we want to decouple that to say, okay, the department should directly depend on the UIE ID. So we move the department to additional table, and now we can access the department type by providing the job ID. So this step, the third normal form, sometimes is excessive so it's usually on the UI we use the second normal form. So it's up to your case if you want to apply that.
So you can quickly access to that, minimize the access skill. Okay.
So if we go back to our messenger example, let's try to convert our non-normalized data, the state of the messenger, to second normal form. So first, we want to reduce the nesting. So we want to remove the conversation and the messages. Let me use the. So we want to remove the conversation and the messages objects from the table. Now we apply the atomic field rules. Now the conversation. Now we store the conversation ID instead of the object, and on the message we also store the conversation ID, and we also create a new type called.
A new type.
Conversation, which has the ID and the title.
So you normalize this, so you don't have nested objects there.
And we also remove the messages from the conversation.
Exactly, because you only want to have flat data, atomic fields, and then the private keys.
Now we identify the primary keys. So for the contact, it will be ID. For the message, it's a message ID. For the conversation, it's also ID. And when we store these fields on the global state, so now
So when we store this as a way to get access to them, so we're gonna store this is like index for that, where this will be now an index of each one of them that they're gonna give you that here.
Now, to access the message with a certain ID, we just provide an ID, and it will return us the message. The same for conversation and for the contact. So although you still may notice that to find specific
So to find a specific message here, we need to traverse the message because this is plural.
message in the array, we still need to traverse all the messages. How can we optimize even that?
Exactly. Minimize now the search cost. Okay. How think of by transforming that into an array, right? By getting the index that we want or the key. So by knowing that key, this is message entity, this is message, the message.
So let's move on to the second principle, minimum.
So how can we achieve this then? Exactly by using something that we can access quickly, some sort of database or data structure that can help me with that. Okay.
Minimize the search cost. So we could potentially build a new an index table, which we'll call inverted index table. It's called inverted because the content of the entity becomes the key in this sense.
Inverted index content.
So what we're gonna do, we're gonna extract all the words from the message content, and then we're gonna build the index table where the key is the word from the content of the message, and we're gonna store the ID of the message where this where this content appears, and the timestamp that will help us to sort out search results as in the timestamp order. So later, we can utilize some asynchronous job to build this inverted index table. This can be a web worker that will access the index DB and store it in the storage, or it can be you can use the idle cycle of your event loop to build this index table in your application. But you may notice that, okay, I can search by the word, but what if I want to search by the prefix? Can we improve it even further? And apparently we can. We can build composite keys. We can use the composite key for the inverted index table. So now we're gonna store all possible prefixes of the word and keep the message ID and the timestamp. So if we type in a search bar, for instance, GA, this will give us all the messages where we saw the GA in the conversation thread. You may notice that the composite key itself, so we can store in JavaScript the string as an array because the key should be always a string. That's where the storage comes in. So let's first understand. So before we discuss the storage, let's understand how we're going to manage the memory. So, yep.
So in this example, there's just two messages, but in theory, if you had like multiple messages that started with hey, those would all end up under that single.
Hey, this will all end up into the.
Either
Yeah,
so
so
composite key.
you would have multiple tuples here.
Okay.
So the inverted index table may become large. So for instance, we may have already 1,000 of messages in each conversation thread. So we don't want to blow the memory of the device. So the way how can we optimize that is, so right now we have the conversation with John, but we know that there are two more conversations that are not active. So we can't just select them from the state, since we know exactly the conversation IDs, and we also know the we know the conversation ID, and we can filter out the entries. Now what we can do, we can outsource that to the separate storage. So we move this element to the separate storage, and we basically sharded our data. So it's basically the database concept in the browser, where in the database you don't have the single large DB instance. So you have a shards, and you store your data partially in multiple shards. And when you do the query, you're actually querying from the different shards. The same way happens here, but we limit it to two shards. One is our global state, which is runtime memory, and the second one is our hard drive. So when we move elements to the hard drive, we let the JavaScript engine to utilize all the objects from the memory and free up let the garbage collector free up the space. And for instance, if we selected the new conversation and we want to load the data back to the store, we can utilize the storage to just populate this back to our runtime memory. And we're basically going to swap back and forth the data. And now the question is, what type of storage should I use to achieve such behavior? And let's do the quick overview. So the browser storage API provides three types of storages for us. It's the IndexedDB, local storage, and the session storage. So the session storage is good for storing some small non-persistent data. So it stores things only for one single session. When the user closes the website, the session is destroyed, and you don't have any, and the data is wiped.
Where the
local storage, on the other hand, is good for storing small things. It can be user preferences, you can also store non-persistent data and discard it if you want. But the local storage provides persistence.
Exactly.
But the problem with the local storage and the session storage, they only support the string type, and they're asynchronous. So if you have a data that you expect to read a lot and write, then you will block the UI thread, and it will impact your application responsiveness. So what do we need to do to re-implement the behavior we discussed previously on the slides? So the IndexedDB, on the other hand, has the almost unlimited storage capacity. On average, it's 3 gigabytes. And it also supports indexing. So we can create a composite index we discussed and store the key as a set of prefixes. And we can actually enable this search using the IndexedDB, so we can utilize this index. And also the IndexedDB supports multiple type of data, which is very useful when we store complex objects. And it's also non-blocking. So it uses the so it's asynchronous. It means that we will not block the UI thread in this case. So the summary for application state design is, first you need to know your scale. Always start with the way how you structure your data, and use normal forms to provide optimized access cost, and use indexes if you're planning to do the search operations in your app. If you think that you will need to store a good amount of data in your state, then offload the data to a hard drive. For us as developers, it's basically the free space that we can use, and it will improve your responsiveness of the app. And also, you need to be mindful about the storage, the type, which it's a message ID. For the specific message in the array, we still need to traverse all the messages. How can we optimize even that? So let's move on to access the message with a certain ID. We just provide an ID, and it will return us the message. The same for conversation and for the contact. So although you still may notice that to find specific message in the array, we still need to traverse all the messages. How can we optimize even that? So let's move on to the second principle, minimize the search cost. So we could potentially build a new an index table, which we will call inverted index table. It's called inverted because the content of the entity becomes the key in this sense. So what we're gonna do, we're gonna extract all the words from the message content, and then we're gonna build the index table where the key is the word from the content of the message, and we're going to store the ID of the message where this message where this content appears, and the timestamp that will help us to sort out search results as in the timestamp order. So later, we can utilize some asynchronous job to build this inverted index table. This can be a web worker that will access the IndexedDB and store it in the storage, or it can be you can use the idle cycle of your event loop to build this index table in your application. But you may notice that, okay, I can search by the word, but what if I want to search by the prefix? Can we improve it even further? And apparently we can. We can build composite keys. We can use the composite key for the inverted index table. So now we're going to store all possible prefixes of the word and keep the message ID and the timestamp. So if we type in a search bar, for instance, GA, this will give us all the messages where we saw the GA in the conversation thread. You may notice that the composite key itself, so we can store in JavaScript the string as an array because the key should be always a string. That's where the storage comes in. So let's first understand. So before we discuss the storage, let's understand how we're going to manage the memory. So, yep.
So in this example, there's just two messages, but in theory, if you had like multiple messages that started with "Hey," those would all end up under that single so composite key.
You would have multiple tuples here.
Okay.
Mm-hmm.
So the inverted index table may become large. So for instance, we may have already 1,000 of messages in each conversation thread. So we don't want to blow the memory of the device. So the way how can we optimize that is, so right now we have the conversation with John, but we know that there are two more conversations that are not active. So we can just select them from the state since we know exactly the conversation IDs, and we also know the we know the conversation ID, and we can filter out the entries. Now what we can do, we can outsource that to the separate storage. So we move this element to the separate storage, and we basically sharded our data. So it's basically the database concept in the browser, where in the database you don't have the single large DB instance. So you have a shards, and you store your data partially in multiple shards. And when you do the query, you're actually querying from the different shards. The same way happens here, but we limit it to two shards. One is our global state, which is runtime memory, and the second one is our hard drive. So when we move elements to the hard drive, we let the JavaScript engine to utilize all the objects from the memory and free up let the garbage collector free up the space. And for instance, if we selected the new conversation and we want to load the data back to the store, we can utilize the storage to just populate this back to our runtime memory. And we're basically going to swap back and forth the data. And now the question is, what type of storage should I use to achieve such behavior? And let's do the quick overview. So the browser storage API provides three types of storages for us. It's the IndexedDB, local storage, and the session storage. So the session storage is good for storing some small non-persistent data. So it stores things only for one single session. When the user closes the website, the session is destroyed, and you don't have any, and the data is wiped. The local storage, on the other hand, is good for storing small things. It can be user preferences, you can also store non-persistent data and discard it if you want, but the local storage provides persistence. But the problem with the local storage and the session storage, they only support the string type and they are asynchronous. So if you have a data that you expect to read a lot and write, then you will block the UI thread and it will impact your application responsiveness. So what do we need to do to re-implement the behavior we discussed previously on the slides? So the IndexedDB, on the other hand, has the almost unlimited storage capacity. On average, it's 3 gigabytes. And it also supports indexing. So we can create a composite index we discussed and store the key as a set of prefixes. And we can actually enable this search using the IndexedDB, so we can utilize this index. And also the IndexedDB supports multiple type of data, which is very useful when we store complex objects. And it's also non-blocking, so it uses the so it's asynchronous. It means that we will not block the UI thread in this case. So the summary for application state design is, first you need to know your scale. Always start with the way how you structure your data, and use normal forms to provide optimized access cost, and use indexes if you're planning to do the search operations in your app. If you think that you will need to store a good amount of data in your state, then offload the data to a hard drive. For us as a developers, it's basically the free space that we can use, and it will improve your responsiveness of the app. And also, you need to be mindful about the type of storage you use. Utilize the data properties. If you expected to read the data a lot, use the asynchronous storage. For small things, utilize the local storage or the session storage. And that's it for the application state design.
Very consistent and succinct. Okay.
So let's talk about how we talk to this server. Imagine that we're trying to build the shop administration app with two main endpoints. The one is to track new orders. The second one is to chat with employees. What are the technologies we would use for that? And what is the stack? So let's first overview the protocols available to us. So there are two main protocols. One is UDP. The second one is TCP. The UDP is the protocol that doesn't guarantee the package the package from the server received in the full size. Or you can, so when you receive the data from the UDP, you just request the server, and the server does not ensure that the data is received by the client. So this means there is some data loss in process. This protocol is heavily used in video streaming, where you can lose some data packages throughout the transfer. It will the data, so your video stream quality may lose some bytes, but it's not critical. So it basically provides a response. If the response is not provided, that's fine. The server can continue fire the response. But the TCP is different. TCP ensures that the data requested by the client and sent by the server is received in full.
First.
So for that, it does the three-way handshake. So it basically calls the server with a synchronous package to tell, okay, server, I want to connect with you.
I want you to get.
Then the server sends the sync acknowledge package saying that, okay, client, I can also connect with you. And then the clients finally acknowledge, okay, let's have a conversation now. So this three-way sync provides the kind of insurance that the data between the client and the server is received. So, and then the client makes a request. So, and as you can see this, because we need to do free network trips now, the TCP is generally slower than the UDP. So UDP, the main benefit of UDP is speed, while the TCP ensures the data validity. And there are some branches of these protocols. So the first, and how basically the web runs, is the HTTP protocol. The HTTP 1.1 is based on TCP, and there is also HTTP 2, which is basically the new protocol, but it still inherits the properties of HTTP 1, and it's still backed by the TCP. And there are also WebSockets. So WebSockets slightly different because they do not utilize the HTTP 1. They use HTTP 1 only to initiate the first request for the server, and then they upgrade to TCP. So it's basically the WebSockets are fully TCP based. And there is a server send events that are based on HTTP2, which is the server push technology. And we're going to look at all of these protocols just in a few slides. Then there is a UDP. And UDP, there's a protocol developed by Google called Quick. And Quick is using the UDP under the hood. And the new protocol, HTTP3, is actually based on the Quick, which is based on UDP. So we are moving from TCP to UDP soon for the HTTP3 protocol. And also there is a WebRTC, which is used for the streaming. And even this stream now is streamed probably through the WebRTC now. Okay, let's get back to the examples with our with our application example. So we have the first endpoint, getting new orders. So how would we design this? So the first thing that we could use is the technique called long polling or short polling. It's basically making the normal get call every specified time frame, for instance, every 20 seconds. And it's very easy to implement. So we can set up the interval and use the fetch request and call the server every 20 seconds.
Making a request.
So what are the issue of the long polling for getting new orders? So the first one is the HTTP protocol. Since we need to establish the three-way handshake with the server, it's relatively slow. It will be pretty slow. And when we establish the HTTP connection, we open a new TCP and call the server every 20 seconds. Mm-hmm. So what are the issue of the long polling for getting new orders? So the first one is the HTTP protocol. Since we need to establish the three-way handshake with the server, it's relatively slow. It will be pretty slow. And when we establish the HTTP connection, we open a new TCP socket. And TCP socket apparently takes CPU, and it also drains energy as a result. And it also has the property of an efficient network usage, because when you establish the connection with the server, you send the metadata, which is the headers, with the request. And if you are on HTTP 1, then the header data is not compressed, and you may end up sending 50 kilobytes every request of just header data. And HTTP 2 improves the situation by compressing the headers, but we still have this three-way handshake that we need to establish. And there is one thing is that the long polling and short polling actually drains the battery of the mobile devices, because you need to maintain your TCP socket open. And when your TCP socket is open, the key thing how the mobile module is structured. So in your phone, you have your mobile network module has two modes. One is mono. It's basically receive only. When this module in the receive only mode, so it's very energy efficient, but it can only receive the data. But there is also a duplex mode where you can send the data and receive the data, and it's not energy efficient as a result. So when we use the long polling, the mobile device utilizes the duplex antenna. So it receives the data and sends the data. And if we run the quick experiment, for instance, we have the 2000 battery, and we know the average energy drain. So
the average energy cost, timeout 30 seconds, time frame 5 minutes.
Takes only almost 4 hours to drain the full battery by maintaining just one socket opened. And I attached a link to the research paper that you can use to.
Holy hell. Okay, that's quite interesting. An energy efficient solution of web-based communication in Android phone. Open access. So this is the abstract. Summary of HTTP protocol. Poly from browser, okay, is internally needs to make an HTTP request every X amount of time, okay, which means that the server needs to first, in this TCP connection, do the handshake. Hey server, I need to talk to you. The sync, which is the package, send it to a package of the letter, send it to the server from the client and say, hey, I need to talk to you. The server received that. Can you talk to me? And then the server can decide to yes or not, but most of the time yes. It say, okay, yes. Let me now sync and enact this letter to you. The client receives that acknowledge from the server and say, okay, so now let me actually send you an ACK as a way to now start our conversation. Oh, and this is a process that is repeating over and over and over and over, and every time you create is a connection, they have to do this. A connection, which a TCP connection. Mhm. However, polling, despite its simplicity, has a prior drawback. The resources consumed by the client, browser processing, and the network strongly depend on the frequency data are updated. Mm-hmm. So unlike WebSocket, a WebSocket button for simple polling, the client has a function poll server in Figure 2 that every interval sends a request get function in jQuery and immediately receive and process the response. The client must establish, usually hard-coded, the polling interview which determines when the server is polled by the fronting of the application, indicated by the clock in the upper code in the Figure 2. Long polling. In order to improve polling shortcomings, there are several server-side programming mechanisms, often grouped under the common label Comet. Well, one of the most common server push mechanisms is HTTP long. Okay, one of the most common server push mechanism is HTTP long polling, in which the server attempts to hold open, not immediately reply, each HTTP request, responding it as sending the HTTP response. Only when there are events to deliver, then there is always a pending request to which the server can reply, sending data as it is available. This solution enables a web server to send data to clients when new data are available, and the browser does not have to be aware of polling periodically, nor adjusting the polling interval. Long polling can deliver updates to browser in a timelier manner while avoiding the latency experienced by client's application due to the poll interval or empty responses, thereby minimizing the latency in message delivery and the use of processing network resource. So long polling can deliver updates to the browser in a timelier manner while avoiding the latency experienced by client application, giving a compliant server supporting async servlet and the compliant browser, and send the request code shadow in blue in my middle Figure 2. Long polling serverlet do this because they're using is this API, XML HTTP request, long polling. Once the server has new data available, it completes the HTTP interaction, sending the corresponding HTTP response. The basic communication cycle of an application using HTTP long polling is as follows. Figure 2b. Exactly, this is long polling. JavaScript code for polling, long polling, alright, is because now they're using is the XML HTTP requests or XHR with the long polling servlet, okay? And the server must integrate that for that. And the other is the WebSocket protocol. Energy profiling tools. Empirical study and data collection. Energy consumption for polling, joules, 200 joules, god damn. Okay, of course, every 1,000 milliseconds, which is every second, of course, it makes sense. Every 50 seconds. 25 joules for experiment of 5 minutes. According to our experiment, there are different patterns of energy consumption. This is energy consumption on polling for 1 minute. Energy consumption of polling 1 minute in Chrome Firefox, in Chrome A, Firefox, and 5 minutes experiment in Chrome and Firefox. And this is 1 minute. In Chrome and in Firefox. God damn. And then a 5 minute experiment. Energy consumption for polling for 1 minute experiment in Chrome. A and B. Okay, this is 1 minute and 1 minute, 5 minutes and 5 minutes. But this is for WebSockets. And this is one of them is for short polling or polling. Exact polling, and then you have now long polling. Firefox sucks. Chrome 5 minutes, and this is now using WebSocket. Jesus, wait a second. This is long polling. Okay. Damn, son, this is using long polling. God damn it, bro. Okay, that's quite interesting. Long polling in WebSocket. Energy consumption in joules of random experiment. Okay. Answer to research question. This is like the data point. Mean standard deviation, minimum, maximum. Polling, long polling, and WebSocket. Box plotted as the energy consumption for polling. Polling, long polling, WebSocket. Firefox 1 minute experiment. This is in Chrome, in Firefox, long polling in Chrome, long polling in Firefox. Threats to validity. conflict of interest. The author declared that they are not conflict of interest regarding the publication of this paper. Conclusion of future works. There is a scenario that can be considered the greenest. There is no scenario that can be considered the greenest one of their difference of power consumption. So, accordingly, exactly, a test of 5 minutes for 30 seconds on a battery of 2000 milliampere, it says that maintaining maintaining an open active connections for long polling, it draw an estimate of drying the battery life in 3.7 hours.
If you're interested in reading the whole paper. So this is the problem number one, CPU utilization and energy drain. So this is not an issue for desktop apps where we don't think about the battery of the device because we are connected to, we are plugged into energy network. But this is a big deal for the mobile devices where we need to be very network and energy efficient because we have limited network bandwidth and the battery. The second problem is the latency. The long polling and short polling latency can be an issue on mobile devices. And this happens when, for instance, you're on the fast train or in a fast car, and then you're connected to some network tower. So then you sit on your train, you may end up losing the connection and reconnecting to the new network tower. So now you need to reestablish the connection again, send the headers, and do the freeway handshake. And if you change your network towers multiple times, imagine that the latency can be significantly increased. And also, the problem with the long polling is that you need to re-implement reconnection. Every request to the server, which is done through the REST API, is stateless. So you don't know exactly. You will lose the state, and you will need to re-implement some infrastructure on the server side to do this. So it's in the long run. For the mobile applications, it's actually costs more to support the long polling, money-wise, of course. So what is the summary then? So the long polling is very good. It's very easy and cheap to implement, and definitely there is no additional infrastructure required unless you work with the mobile apps. If you work with the mobile apps, then there is an issue with that it's not battery efficient because it's used CPU to maintain the TCP socket. And it's also not network and data efficient because you're sending the headers with the request when you do the freeway handshake and when you try to request the data yet you are trying to receive. And if you're on HTTP1, the situation is even worse because HTTP1 sends too much overhead data. And so what is the use case then? The use case is actually for the long polling can be used with desktop apps where we don't care about the network bandwidth and also about the latency because we're stationary. We do not connect to different mobile towers, and also we do not care about the energy drain. So it's also pretty cheap to implement for the desktop users, and it's pretty well suited. But when it comes to mobile web application, then you would need to consider a different technique. The first alternative that we could potentially use to long polling is the server send events. This is the server push technology. So it's a slightly different. So it's based on HTTP2, and the way it works is when you establish the connection with the server, the duplex communication is used only when you do the initial connection, just the initial freeway handshake. But the rest of the connection is basically the server pushes the data to the client.
To see if it's there.
So in case of the server send events, the duplex antenna is not used. We only use the receive-only mode, and we do not drain the energy. Although we still have an issue with the reconnection where we need to do the freeway handshake. But the huge difference with the service end events that the reconnection is implemented on protocol level, so you don't need to handle that on infrastructure wise. So you can always resume from the place where you started. And the huge benefit business wise for using service end events is very easy to scale. So for instance, if we have multiple instances of the server and one instance has died, we can just forward the request to a separate instance. And because we can always resume from the previous place using the service end events, so it doesn't matter for us which instance will respond. So since the service end events is HTTP2 based, it also utilizes the TCP socket differently. We're going to talk about HTTP2 protocol just in a few moments, but the huge benefit of HTTP2 is because it has the multiplexing feature. The multiplexing allows us to open 200 requests within one single TCP socket. So this means while in HTTP1, to fetch 5 resources, we had to open 5 TCP connection, which is much less efficient. So the service end events is generally much faster than long polling because it also doesn't send any junk data. So we don't send any unnecessary headers, and we receive only the data that relates to the content. And the summary for that is there are definitely pros for service end events because the connection is handled automatically. It's very battery efficient from the mobile device perspective, and it doesn't send any the overhead data. And the horizontal scaling of your infrastructure is much easier when you use the service end events. The cons, though, you can't push the data to a server, and only the string data is supported by returning this. So you will need to parse the text payload that you send from the server. And when you need to use it, that's good for both desktop and mobile web applications. And it also provides a very good performance. So the performance is comparable to the WebSockets that we're going to discuss on the next slide. And it's very good for streaming the large text data if you have this case. And the reason why you would avoid this is if you're building very simple desktop app. So then you'll be fine with long polling. You don't need to really overcomplicate the architecture of your app. So the WebSockets is the fastest way how can we transfer the data between the server and the client. So the WebSockets is the duplex push technologies. It means that the client can push the data and the server.
Okay. Let's gonna do something. That'll be all for this video. Okay. Yeah, because this is something that it seems that it's gonna take quite a lot. Quite a lot. And I need to take this bit by bit. Okay. So that'll be all for this video. Take care. Bye bye.